Section 4.2, transformations of initial value problems, IVPs, initial value problems. What are initial value problems?
Initial values.
That's why I give you a differential equation and I give you initial values. That's correct. So what does that mean? We're going to learn how to do this in this section. And what are we going to do with Laplace transforms? We're going to learn how to solve differential equations using Laplace transforms. That was our whole goal behind learning Laplace transforms. In order to do that, we need a theorem. I got to make sure I get the conditions right here. Theorem 1 says, suppose f of t is continuous and piecewise smooth for t greater than or equal to 0, and is of exponential order. Then the Laplace transform of the derivative of f of t exists and is the Laplace transform of the derivative is s times the Laplace transform of the original function minus f at 0, which is quite often written as s times f of s minus f at 0. All right, so we have some new words there, I think. Continuous, that's not a new word. What does it mean to say f of t is continuous? No discontinuities, no jumps, no holes, no vertical asymptotes, no breaks. That's our Calc 1 thing. Of exponential order, we talked about that a few days ago. What does exponential order mean?
Doesn't grow faster than an exponential function?
That it doesn't grow faster than some exponential function. That's correct. So this means there's an exponential function that grows faster than f of t. The new words, I think, here are piecewise smooth. Anybody know what piecewise smooth means? What would smooth mean? Anybody know? Smooth would mean there are no cusps, which means there are no places where the derivative is undefined. That's what smooth means. So what do you think piecewise smooth means? What's that?
Smooth try to give an interval.
It's smooth within given intervals. So what piecewise smooth means is that there are a finite number of cusps. So a continuous piecewise smooth function might look something like this. There might be a cusp there, there might be a cusp there, like so. So this would be a piecewise smooth function. It's continuous. It's all connected. There's no holes, no jumps. Piecewise smooth means there's at most a finite number of cusps, a finite number of sharp corners like that. So there would be an example of a continuous, piecewise smooth, exponential order function. So what this is doing is, this is telling us how to find the Laplace transform of a derivative and put it in terms of the Laplace transform of the original function. Questions about that? All right, so here's the deal. The Laplace transform of the derivative, by definition, would be the integral from 0 to infinity of the derivative e to the negative st dt. How would you integrate that? You would integrate by parts.
You would do like, you can do the tabular method, right?
You can do what?
Can you do the tabular method if f prime of t goes to 0?
I could do the tabular method if f prime of t goes to 0, but I don't really know anything about f prime of t. I don't know what it's going to do. So I'm just going to do some integration by parts here. I'm going to let u be e to the negative st. And then what would du be?
F prime of t.
No, just take the derivative. Du would be negative s e to the negative st dt. And dv would be f prime of t dt. And when I integrate that, I get, that would just be f of t. So, integration by parts tells me I have u times v, that's e to the negative st, times v, that's f of t, minus the integral of v, which is f of t, du is negative s e to the negative st dt. Then I have to evaluate this from 0 to infinity. Well, what happens when I plug infinity in? What happens when I plug infinity into this piece? It goes to 0. How come? And f of t is of exponential order, so it's smaller than an exponential function. So when I plug infinity in here, I get 0. When I plug 0 into this one, I get f of 0, actually, right? Because I'm plugging 0 in for t. But when I plug infinity in, that would be the positive. So that would be 0. Minus, I plug 0 in, I get f at 0. And then here I've got a minus and another minus, that's a plus. So I pull out the s. This is the integral from 0 to infinity of f of t e to the negative st. What's that integral? That's the definition of the Laplace transform. So you do get minus f at 0 plus the Laplace transform of f of t. Oops, with an s out front. I forgot my s. So this theorem is really just a special case of integrating by parts. So if I want to do the Laplace transform of a derivative, I can convert it to the Laplace transform of the original function. What if I want to find the Laplace transform of the second derivative?
Would it be a two-step?
It would be a two-step deal. Well, according to this, I'm going to have, if I started with the first derivative, oops, you can't see what I'm pointing at. If I start with the first derivative and I do the Laplace transform, I get s, and then I get f of t, and then I get f at 0. So what's going to be different when I start with the second derivative? I'm going to have s, Laplace transform of f prime of t, minus, instead of f at 0, I'm going to have f prime at 0.
But then the Laplace transform of the f prime of t is equal to...
But then I can, that's exactly right. I can now use my rule about the Laplace transform of f prime. So this is going to be s times s Laplace transform of f of t minus f at 0 minus f prime at 0. So notice I end up with s squared Laplace transform of f of t minus s times f at 0 minus f prime at 0. What would happen if I wanted to go wild and take the Laplace transform of the third derivative?
Yeah, s to the third times the Laplace transform of t minus s squared f of f double prime 0 plus s f prime 0 minus f 0.
See the pattern here.
He said it exactly right. If I wanted the Laplace transform of the third derivative, Jesse said I would end up with s cubed Laplace transform of the original function minus s squared times what?
F double prime.
F double prime at 0
Yep.
minus
S
s
of prime
f prime at 0
minus f of 0.
minus f of 0. And I could go on and I could do third derivative, fourth derivative, fifth derivative, on and on and on. But you get the pattern. What happens is you get the s cubed, then the s's go down, and on this end you start with f, and then you got derivatives going up.
Can you go back to f double
I would love to go back to f double prime. Yeah, I think Jesse made a mistake there.
Yeah, I was confused. You're good.
Oh.
It should be just
Wait.
f double.
So notice your s's start big, s's go down, s squared, s, no s's. And then notice you start with f of 0 here, and then your derivatives start to go up.
Oh.
So we got it backward. So this one should be f, this one should be f prime, and this last one should be f double prime. The s's go down in powers, the derivatives go up in powers. So it should go from up through.
You knew the answer.
All right, so this is page 287, number 4. We have x double prime plus 8x prime plus 15x equals 0. And we have two initial conditions. X at 0 is 2 and x prime at 0 is negative 3. I'm going to take this equation and I'm going to do the Laplace transform on both sides. So according to that theorem we just had just a second ago, what's the Laplace transform of x double prime?
S squared Laplace transform of x.
S squared Laplace transform of x minus s times, in this case, x of 0, which is the number 2. I'll plug in the number 2 in just a minute here. Minus
Minus f prime or x times 0.
minus x prime at 0. So there's the Laplace transform of x double prime. Plus 8 times, I have to do the Laplace transform of x prime. What's the Laplace transform of x prime? S Laplace transform of x minus x at 0. In this case, we're using x instead of f. Plus 15 Laplace transform of x equals, what's the Laplace transform of 0?
X.
0. Laplace transform of 0 is 0. You should have the integral of 0 times something. That would be 0. Okay, so I'm going to do a little simplifying. I'm going to write this as s squared. Instead of writing the symbol Laplace transform of x, we typically call it capital X. So notice we started with a little x. Little x has a variable of t. When we do the Laplace transform, we write it as capital X, which has a variable of s. Minus s times 2, so that's 2s.
Wait, I'm sorry, can you explain again? What is capital X of S?
Capital X of s is just another symbol for the Laplace transform of x.
Okay.
It's just quicker and easier to write.
It's just like when we did capital F of X, or capital F of X.
Correct. When we started with f of t and we found its Laplace transform, we had this integral 0 to infinity, e to the minus st f of t dt. When we got all done, we tended to call that capital F of s. So same deal here. I'm starting with x of t. When I take its Laplace transform, I'm going to call it capital X of s. Okay, so I had s squared, capital X, minus this x0 was the number 2, so that's a 2s, minus x prime is negative 3, so that's minus negative 3, that's plus 3, plus 8s, capital X, 8 times the original function, that's 8 times 2, that's minus 16, plus 15, capital X, equals 0. What to do next? Any thoughts?
Instead of capital F, as one would screw that in for 1 over X. Laplace transform of X, isn't that 1 over S?
The Laplace transform of t is 1 over s.
Oh.
This is already a Laplace transform. I already did a Laplace transform to get this big X. Eventually I'm going to want to get rid of the big X. If this is a Laplace transform and I want to get rid of it, what do I have to do?
The anti-Laplace?
An inverse Laplace transform eventually. Correct. So what I would like to do is I would like to do some algebra at this point, and I would like to get this capital X all by itself equal to something, and whatever this something is, I will then do an inverse Laplace transform, and that will give me my little x back. All right, so the algebra I think I want to do is I see that there are 3 things that all have the x of s in them. So I'm going to put those together, and I'm going to write this as s squared plus 8s plus 15 all times my capital X. And then these things which do not have capital X, there's 3 of those, I'm going to move those over to the other side. So when I move those over, that's going to be equals 2s plus 13. Because negative 3 plus 16 is negative 13. But when I add it to the other side, it's a plus 13. So now I'm going to divide. That's right. So x of s is 2s plus 13 divided by s squared plus 8s plus 15.
with an S, so it doesn't look like a 5.
Because I thought that was 25.
Or like cursive S,
They
maybe.
got me a double thing. Why would they pick something that looks like a 5? This is a poor choice.
Well, back then,
It's the standard letter. I don't know why it's S. It's the standard letter.
Cursive S or something or something. Show it's a little different.
Yeah, I write carefully, I guess, so you can read your own writing. I guess would be the moral of the story. All right, now the big question is, how do you find the inverse Laplace transform of that thing? Factor the bottom. So that's 2s plus 13 over s plus 3, s plus 5. So I wrote my s small and my 5 big so you could tell them apart. How does that help?
Doesn't.
It doesn't?
Wait, you could probably separate it.
Separate it how?
The 2s plus 13 over s plus 3 and 2s plus 13 over s plus 5.
Oh, you certainly can't separate it like that. In order to add fractions, you got to have a common denominator.
S squared plus 8s plus 15 plus 13 over all that.
I can separate the top, but I don't think that helps. Because I'm looking at my list of what I know for Laplace transforms. See this list that I have? I noticed that I could have an s on bottom or an s squared or an s cubed or something like that. If I had an s minus a on bottom, that would be helpful. That would be an e. I don't see anything that has a product like that on bottom. I looked all the way through the list. I didn't see any. What about that thing you learned in Calculus 2? What a wonderful idea. What's that thing you learned in Calculus 2 called?
Oh, you just separate.
It is called partial fractions. Very good. That would be very helpful, because once I have just an s plus 3 on bottom, I could think of that as s minus negative 3, and I could do my inverse Laplace transform. I'm going to get an e. All right, so welcome back to Count 2 again today. Partial fractions.
taking count 2 just before this class.
All right, so we're going to have, I got to make some more space here. 2s plus 13 over 3 times s plus 5 equals a over s plus 3 plus b over s plus 5. And then for partial fractions, what you did is you cleared the denominators. So you took this whole thing and you multiplied by the common denominator, s plus 3, s plus 5. So you have 2s plus 13 equals a times s plus 5 plus b times s plus 3. Then what did you do?
You put in zero, like a 0 for A to get B, and then you put a number in for like A to get B, and then you put
I picked my favorite number in the whole wide world for s. 2, nope. 0, nope. Negative 5 is one of my favorite numbers in the whole wide world. Why negative 5? Because it makes this whole piece 0. When I plug in negative 5, I get 3 on the left-hand side equals b times negative 2. So b is negative 3/2. And then I plug in my second favorite number in the whole wide world. For this problem, my second favorite number is negative 3, because when I plug negative 3 in, it makes that whole part go away. Plug in negative 3, I get 7 equals a times 2. So a is 7/2. Okay, so we're almost done. So instead of a, we've got 7/2 here, and instead of b, we've got negative 3/2. Now we're ready to answer the question. The answer to the question is little x of t, the original function we started with. I do the inverse Laplace transform. I'm going to have 7 halves e to the negative 3t, because I'm using my cheat sheet here. S minus negative 3 on bottom, that's e to the negative 3t right there. Oh, I don't have to integrate. This was a theorem that we proved already, that the Laplace transform of e to the at is 1 over s minus a. So the inverse Laplace transform of 1 over s minus a is e to the at.
How do you like write it?
How do I write it? I write it just like that. And then minus 3 halves e to the minus 5t. What's that?
It is a new way.
That was the new way. All right, so what did you learn? You should have the cheat sheet that I have. Yeah, you should have the cheat sheet that I have. That's right. What else did you learn?
We learned to use Laplace transforms to solve differential equations.
We learned to use the Laplace transforms to solve that differential equation. Let me ask you a question. Could you solve this differential equation with the knowledge that you learned in Chapter 2?
Yes.
In fact, you would tell me that it's r squared plus 8r plus 15, which factors as r plus 3, r plus 5. So you're going to get an e to the negative 3t and an e to the negative 5t. Plug your numbers in, solve for C1 and C2. So what's the moral of the story?
Why are you giving us harder problems? Go back.
It works.
The moral of the story is we're not done yet. Remember, back in Chapter 2, in order to solve, we always had to have constant coefficients. So we're not done with Laplace transforms yet. In the near future, we'll talk about what if you don't have a constant coefficient. What if you have t there? Then you cannot solve it with what you learned in Chapter 2. So this is part of the building blocks. I agree that solving this differential equation using Laplace transforms is a whole heck of a lot harder than what we learned in Chapter 2. But you need to be able to do this before you can do the problems which have non-constant coefficients, which we'll be getting to in the near future.
So tell me again why we skipped Chapter 3 to jump to Laplace.
Because Chapter 3 is a technique for approximating solutions, not for finding exact solutions. So we will come back and we will do Chapter 3 and Chapter 6 together, because Chapter 3 and Chapter 6 are both approximation techniques. No, I mean 6. 5 is something completely different altogether.
So why would we want to approximate an answer?
Because sometimes you can't solve it exactly. There's no technique that works. So the best you can do is come up with an approximation. Okay, we will do some more examples of this on Monday. Like 15 of them. I don't think I would have time to do 15 of them in one class. We will do some more examples of this on Monday.